Hello and welcome to this free preview lecture series of my PE Power exam preparation course. In this lecture, we are going to discuss reliability and specifically reliability indices, which belongs to general power engineering with an application subsection. Reliability is an interesting concept and it is not necessarily applicable only to power systems engineers, but you will find that if you're working in heavy industry and consultancy or in a technical role, the word reliability will be thrown around. And for practical purposes as well, it is good to know what exactly some of these indices like failure rate, mean time to failure, mean time to repair, and things like that. So if you get a good understanding of these fundamental concepts, you will not only be exam ready to handle these questions on the exam, but you will also feel more comfortable doing root cause analysis and failure mode analysis, especially in a reliability and maintenance role or working on a project where these things are important. Before we dive into the content, I would really appreciate if you could like this video, subscribe to the channel, and click the bell icon if you haven't already done so. Hello and welcome to part 2 of our multi-part lecture series on the topic of reliability. Learning objectives of this lecture include discussion of general reliability indices, which are mentioned on pages 22 to 23 of NCEES Power Reference Handbook. But we will also do a quick review of utility reliability indices, which cannot be found on these pages, but they're good to know. And finally, we'll take a look at IEEE Standard 493, which discusses recommended practices for design of reliable industrial and commercial power systems. We will start our discussion of reliability indices with one of the most basic index, and this is failure rate. Failure rate is indicated by lambda, and it is simply the number of failures divided by total operating time of the units. Now, total operating time of units, it might be a little bit confusing to understand, but we'll do a couple of examples and it will be clear. So it's very important to understand failure rate. We will do a few examples, as I said, and that will make sense. But let's take a look at this bathtub curve. When you review reliability, you will probably, if you look at some text references and do some independent research, you're most definitely going to come across this bathtub curve. So this bathtub curve basically indicates the reliability of the equipment or the failure rate versus time. So the first small segment is called the infant mortality, and the second section is the useful life, and the third section is the wear out. Now it takes the form of a bathtub because at the onset, at the start, when you're doing commissioning or startup, those of you who have done electrical commissioning would probably be able to attest to this fact that a lot of times equipment, especially some of the major electrical equipment, transformers or switch gears and MCCs and breakers, they tend to fail right here, just when you're starting them up. So you would have done FAT. Sometimes they actually fail the factory acceptance testing. Sometimes they fail site acceptance testing, and sometimes they actually fail the first energization, or sometimes they fail within the first week of operation, right? So this infant, when they're in infant stage, when they're in the very initial early ages, early period of time, the failure rate tends to be very high, okay, as an overall percentage, right? But then as the unit goes in operation more and more, that failure rate essentially drops to probabilistic values. Now this bathtub curve is used for human age as well. So when a kid is born, when a baby is born, the chances of baby passing away are highest in those first few months, and it can be extended up to when the baby is a toddler or up to 10 years old. Basically, historically, there used to be a very high infant mortality before the onset of modern medicine, and it still is the case in a lot of developing countries or underdeveloped part of the world, where babies unfortunately pass away quite shortly after birth or during birth. So the chances of a human life being lost is very high at when humans are infant, right? But then as you become an adult, right, which is this phase, then probabilistically the mortality rate drops, right? And it is lowest up until you hit a certain point where you start aging. And when the process of aging becomes aggressive, then due to the natural aging, people pass away. And so human life also takes this bar-top curve. So moving on to the useful life of the equipment, when the equipment has been operational for some time, right, when you are jumping from this phase to this phase, now the probability of failure is lowest. It is amongst the lowest. Now, where exactly it sits on the y-axis would be a factor of how good or bad maintenance you are doing. So if you're doing bad maintenance, your curve might actually look like this. During this stage, it might be shifted upwards. And if you're doing really good maintenance, it might actually be lower. So it's all stress-related failure, right? So if the unit is not very stressed, then the failure rate might be lower. If the unit is stressed beyond its rating, then it would be you would just fast track the process. And then ultimately, everything is bound to fail eventually. And as the time goes on, the probability of failure becomes higher and higher. So this is the bar-top curve. It is very good to have an understanding of from a high-level point of view, because it gives you the big picture overview of how reliability works as in terms of the life cycle of equipment. And as I said, if you just Google bar-top curve for human life, you will come across a similar curve with probably very specific data on infant mortality and then useful life and then wear out, and you'll probably be able to look at it for different countries as well. But essentially it will take a similar shape. The threshold points might be different depending on which part of the world you're looking at, but for the most part the shape will be exactly the same. Let us now take a look at a practice problem involving failure rates. So we have 8 MCCs that were tested for 200 hours each. 2 MCCs failed. The first MCC failed after 100 hours of service, and second MCC failed after 150 hours of service. So we are being asked to calculate the failure rate of these MCCs. So we know that the failure rate is given by this equation, where lambda is equal to number of failures divided by total operating time of units. Now, total operating time of units is a more difficult quantity to calculate in this case. Some students will probably go ahead and attempt 200 multiplied by 8, which is 1600 hours, which is incorrect, because total operating time has to take into consideration even the units that failed, right? If they failed right away, then obviously that's going to be 0. But in this case, we are given that the first MCC failed after 100 hours, so it contributed towards the total operating time of 1 multiplied by 100, and the second one failed after 150 hours, so this would be 1 times 150, and the remaining 6 passed the test and they continued operating for 200 hours each, so that's 6 times 200. So the total operating time was 1450. Number of failures is pretty simple, straightforward. We know that the 2 MCCs failed, so the lambda is equal to 2 divided by 1450, which is 0.00137 failures per unit hour. Now we will continue our discussion on reliability indices. So the first index that we are going to review is mean time to failure. So the indices that I'm going to discuss now are mentioned on pages 22 to 23 of NCEES Power Reference Handbook. Mean time to failure, or MTTF. This is average length of time before a failure occurs, and it is mathematically equal to the inverse of the failure rate. So failure rate is lambda, so MTTF is simply equal to 1 divided by lambda. After that, we have mean time to repair. Obviously, this is applicable to repairable items only. If an equipment is not repairable and it fails, then it's basically done. This is the average length of time to repair a failed item. Then we have mean time between failures, abbreviated as MTBF. This obviously is applicable to repairable items as well. This is the average time from uptime after repair to the next failure. It determines how often failure occurs, and it is basically the sum of MTTF plus MTTR. Availability. In the earlier lecture slide, we've already defined reliability in terms of availability. It's basically the total number of hours of operation in 1 year divided by the total number of hours in a year, which is 8,760. But in terms of the indices that we've just introduced, MTTF, MTTR, and MTBF, availability can be expressed as the ratio of MTTF to the sum of MTTF plus MTTR, and we know that MTTF plus MTTR is equal to MTBF. So availability simply becomes MTTF divided by MTBF. Downtime per year. Downtime per year is also a key performance parameter. It is fraction of time a piece of equipment is unavailable for use each year. Basically, the total hours of downtime in 1 year divided by 8,760. But in terms of the indices that we just introduced, it is MTTR divided by MTBF. Let us now go through a few practice problems in order to put our understanding of reliability indices to use. So this is problem number 2. A welding machine is expected to operate for 1,000 hours after repair, and the mean repair time is expected to be 4 hours. We are being asked to calculate its downtime per year. So there are a couple of pieces of information that are provided to us in this question. The first one is the MTTF, which is mean time to failure. So between the repairs or after a repair, the welding machine can operate for 1,000 hours. So this is mean time to failure, 1,000 hours, and it takes 4 hours to repair the machine or the welding machine. So it means that the MTTR is equal to 4 hours. As we know, mean time between failures is equal to MTTF plus MTTR. So that is 1,000 plus 4, which is 1,004 hours. Now the unit downtime, which is a fraction of time the piece of equipment is unavailable, it's simply the ratio of MTTR to MTBF, which is 4 divided by 1004. It gives you this number. And downtime per year in terms of the number of hours per year is obtained by multiplying this by 8760, which happens to be the total number of hours in a year. Problem number 3 is asking us to calculate the availability of given welding machine based on the details that are provided in problem number 2. As we saw earlier, availability can simply be calculated by dividing MTTF by MTBF. So we know that MTTF, the mean time to failure, is 1,000 hours, and MTBF, we just calculated in the previous problem, was 1,004 hours. So when you divide 1,000 by 1,004, you get 0.996 or 99.6%. So these next set of reliability indices that we are going to look at are more frequently used by your local distribution company, and it has to do with the level of customer service. So the first one is System Average Interruption Frequency Index. It's quite a long description for a reliability index. In short form, it's called SAIFI, and it is simply the sum of all the customers that are interrupted divided by total number of customers that are served. So NI is your total number of customers that are interrupted, and NT is the total number of customers that are served. And it is essentially the frequency that an average customer is subjected to sustained interruption over specified period of time. So after that, we have System Average Interruption Duration Index, SAIDI, and it is a total duration of interruption an average customer is subjected to over a specified period of time. In this case, we basically multiply Ri with NI in the numerator, and your RI is the restoration time in minutes. So that is how long each outage is going to last, and you divide it by the total number of customers that are served. We also have customer average interruption duration index, CAIDI, which is very similar to the previous one, but it is average time required to restore the service, and it is RI times NI. It is the sum in the numerator divided by the total number of customers that are interrupted. And the last one is your average service availability index. It looks a bit complicated when you look at the mathematical formula, but it is essentially the ratio of total number of hours of service that was during which the service was available to number of hours of service that was expected. It's very easy to comprehend. So if you expect 8,760 hours of uninterrupted service, but you only got 8,000, so essentially it is the ratio of the total number of service hours of service that you received to the total number of hours of service that you expected. And we'll go through a few examples to make all of these indices for them to make more sense. Let us now work through a practice problem involving reliability indices. So over here we are given a table which is outage data, annual outage data recorded by a utility. So the utility had 5 outages, and the total number of customers that are served by the utility are 20,000. And we have some details regarding each of these outages, and we're being asked to calculate these reliability indices. So for example, in outage number 1, we had 20 customers that were impacted. The duration of the outage was 60 minutes. So the number of customer hours was basically 20 multiplied by 60 minutes, which happens to be 20 times 1 hour, because 60 minutes is equal to 1 hour. So 20 times 1 hour. So the total number of customer hours were 20 hours. In the next outage, you can see that we have 500 customers impacted for half hour or 30 minutes. So the total number of customer hours was 250, and so on. So the total number of customers that have been impacted through all of these outages are 526. The total duration is 375 minutes, and the customer hours are 281.25. And we will now use the formulas that we've looked at previously in order to calculate these indices. Now we can go ahead and calculate all of these indices. The first one is SAIFI, which is a summation of NI divided by NT. So summation of NI, I've already calculated it over here, is 526. So these are the total number of customers that were impacted, divided by the total number of customers that are served by the utility. So you will get this answer. SAIDI is a summation of RI times NI. Essentially what you're going to be doing over here is multiplying this column, so number of customers, by the duration, and then summing all of them up. So I have already done that for you. It is 281.25 hours. You just convert it into minutes by multiplying it by 60. The total number of customers that are impacted are 20,000 customers. So you will basically get 0.84 minutes per customer. CAIDI is very similar to SAIDI, and over here we are basically dividing the same number that we got over here in the numerator, which is 16,875 minutes, by the total number of customers that are impacted. Okay, so the only difference is that we have in the denominator for CAIDI the total number of customers that are impacted. In SAIDI, the denominator contains the total number of customers that are served. And once you've calculated SAIDI, you can calculate ASAI by simply using this formula. So 8760 minus SAIDI, we are dealing with annual data, so the time frame is annual, so 8,760 hours in a year, and you multiply it by 100 to get the percentage. And finally, I would like to briefly discuss IEEE 493 2007. This is one of the color book series. It's a golden book, and as you know, I'm a big fan of IEEE color book series. This is titled as Recommended Practice for the Design of Reliable Industrial and Commercial Power Systems. It has a lot of very interesting and useful details. It has a lot of calculations, a lot of examples. So if you're interested in system reliability, I would recommend you to go through it or at least skim through it. So there are a lot of very technical details that are provided in this standard. We are not going to go through it, but at a very high level, it provides you a framework, a stepwise framework, which we are going to discuss over here as to how you can improve the reliability of your distribution system, whether it's industrial or commercial. So the first step is to establish current condition of facility. You'd be surprised as to how many facilities don't even have a good handle, or how many operations and maintenance engineers don't start out with a very detailed catalog of what the condition of every piece of equipment is, because in a lot of cases enough attention is not dedicated towards it, right? So the first step is to understand what you're dealing with. So establishing current condition of the facility. It can be in the form of an audit, okay, of different pieces of equipment, and once you have that database, then you know what you're working with. Step number 2 is to determine the likelihood of serious problem based on this condition. So once you know what the status is, then you do analysis on it and see that, okay, what are the probabilities that we can have critical failures. And step number 3 is to find the equipment which is most at risk to cause problem. Now, this is a very important point. I'd like to spend some time on it. So they're asking you to arrange the equipment in the order of being most at risk to cause problems, not necessarily being most at risk to fail. So if an auxiliary piece of equipment fails, which has little to no impact on the overall facility, on the overall process or production, then even if its probability of failing is very high, it is not most at risk to cause problem to the overall system. So it can be considered disposable, right? But that you would only be able to decide once you understand the entire system. So they want you to list those equipment that can cause serious outages or impact to some critical components of your system. And finally, you have to identify the predictive techniques that give early warning of problem at that equipment. So once you've identified, okay, I have 1 MVA transformer, which if it fails, then you know the entire line is going to go down, right? And I have this particular switchgear which is feeding some critical loads. If those loads fail, then if this switchgear fails, then I don't have any backup. So I need to be able to make sure that I have some plan for this switchgear. And if an MCC is feeding some critical loads, so on and so forth. So they recommend that we have predictive techniques, whether it is routine testing on that equipment, whether you have some online monitoring, so that you can get some early warning signs. So if a transformer is about to fail, you do dissolved gas analysis on the transformer on a frequent basis, especially if this transformer is nearing the end of life, so that you can see how the content of different gases is in the transformer, and before it fails you can actually replace it. And similarly for the switchgear, you can have temperature monitoring on the bus work. You can have temperature monitoring around the circuit breakers, so that you get to, and you can monitor it on live basis, or you can have some sort of thresholds established. There are a lot of different solutions that are provided that are now available. Then you will be able to identify that, okay, this equipment is about to go, and before it reaches the end of life, you can replace it or come up with some other mitigation measures. So the general rule of thumb is that being proactive in the long run, is far better than being reactive. I think we all know that, but it also makes very sound economical sense, because the amount of money and time and effort that you're going to spend in implementing all of these steps upfront is going to be minuscule when you compare to the cost that you would have to pay by being reactive. So if you have an outage on an automotive plant for a day, I mean, they have calculations for per minute basis as to how much it costs them to shut down a line, right? Similarly, any other manufacturing facility, whether it's pharmaceutical, whether you are beverages, dealing with beverages, whether you are in steel industry, any type of manufacturing facility. So taking a line out of production is far more expensive than doing all of these things upfront and making sure that you are proactively working on improving the reliability of your industrial or commercial power system. If you found this preview lecture helpful, I'm confident that you will also benefit from the full course that contains more than 150 lectures and covers all the topics that are found in the latest NCEES PE Power exam specification for the computer-based testing format. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. Once you enroll, I will schedule a one-on-one Zoom call with you to develop a custom study plan based on your schedule and time constraints. On top of all of this, I have also included a special discount link in the text section of this video for you.